In this lecture, we're moving into this new notion called a product measure, and eventually we're going to the Fubini's theorem. As you probably learned in just Riemann integral or in multivariable calculus, the Fubini theorem allows you to interchange the integral of a Riemann integral, and we're going to do the same for the integration of a general measure space. Okay, so that's our goal. So let us first define what does it mean by a product measure and what's actually a product space, okay? So suppose we have some space, let's say lambda in lambda, x lambda, each of them is non-empty, so we don't care about empty space. So the product space is basically the product of them, so you've probably already seen the definition in somewhere, maybe in 351. So this is essentially all the, you can think about it two ways. So one way is all the collections of some little x lambda. Okay, so you can think about it as well, here lambda is really large, it's just the index set, so you cannot say it's a sequence, but it's something like a sequence where each of these entry x lambda is inside the space x lambda. Another way of thinking this is you can treat it as a function. You treat it as function defined on the index set. And the range is basically something in the x lambda. Here you treat x lambda as disjoint sets, okay? Even though they may be the same, but you just treat them as different copies of x lambda. And the requirement here is the image of each of these index f lambda is going to be mapped inside the lambda copy of x, the correct copy. So you might as well just give it a name called a little x lambda. Okay, so you can see they're really the same definition. Okay, so for product space, one of the most important map is the coordinate map. So let's call the little pi. So let's do the little pi of lambda. So if I'm given such a collection of x lambda inside this product space, so maybe let's do the lambda naught here just to differ. So the coordinate map is basically I ask the coordinate on this lambda 0, so I return the value on the lambda 0 copy. Okay, so this is called the coordinate map. So if you have taken, I know some of you are taking functional analysis this term, you probably will see it or already seen it in functional analysis, where you kind of start with some topological space, x lambda, and you want to induce a topology on the product space. The way you do it is you say, well, let's let these coordinate map be continuous, and that will induce a topology on the product space. And this course we're on measure theory, so we don't have topology yet. So we care about how we induce a not a topology, but induce a sigma algebra on the product space. So let's start with some measurable space. So suppose each of these x lambda, you can put some sigma algebra, so they are measurable space. So as an analog of what you see in the product topology and function analysis, we want to induce a sigma algebra on the product space. Okay, this is done by just doing something we actually seen it on your first assignment. So let's give some definition. So let's call it a cylinder set. Is essentially just the inverse image of some x lambda of A, where A is inside the sigma algebra on the lambda copy. Okay, so one way to think about it is that on the lambda copy, so here is on x lambda, you put A, and on everything else, you put the x lambda. Okay, so x lambda prime and so on. Okay, so for example, if let's just take if you have Rn, then what the cylinder set, it looks like A cross R cross R. The A can be the first copy, but it can also be the second copy. Okay, so you only allow one of them to be something different, but that something different has to be in your sigma algebra. and everything else has to be the entire space, okay? And I already put this on your first assignment where if I require A to be a closed interval or Rn, I call it a closed cylinder, okay? So that's where this definition came from. So let's define all the cylinder set. Let's just give it a name. Let's call it C to be the set of all cylinder sets. So essentially, that's just all the pi lambda inverse of some A, where A is inside B of lambda. Here, lambda can be anything. Okay, it doesn't have to be a fixed lambda. Okay, so all of these cylinder sets, well, they are just some sets inside the product space. So what do? We can generate a sigma algebra. So this is called the product sigma algebra. So definition. The product sigma algebra. Let's give it a notation. Let's use this O times. Okay, so you have a times and you put a O there. Sometimes also call it a tensor. Okay, so we're tensoring or O times all of these B lambda. Okay, so here B lambda are the sigma algebras. Let's just define it to be, by definition, that's the sigma algebra generated by the cylinder sets. Okay, so C is the collection of all cylinder sets, and they generate a sigma algebra. We call it the product sigma algebra. So when I just want to remark, when lambda is actually finite or countable, this product sigma algebra can also be generated by a box. Okay, so what I mean is define a box is just a product of some A lambda, where lambda in lambda, where each of these A lambda is inside the corresponding sigma algebra. So let's call these boxes, and apparently each cylinder is a box because cylinder set is just one of these A lambda is not equals to X lambda. On the other hand, when lambda is finite, these boxes, or when lambda is countable, this is the intersection of the cylinders pi lambda inverse of the A lambda, okay? So here, lambda in lambda. So this is a countable or finite intersection as long as your index set is finite or countable. So it's inside the sigma algebra generated by the cylinder sets. So all of these boxes are measurable in the product sigma algebra. And you can see the converse as well. So when the index set is finite or countable, then automatically you have the sigma algebra generated by the boxes. It's also this product sigma algebra. Okay, so do the B lambda. Okay, so they are the same. Okay, but in general, when lambda is uncountable, this is not the case. Okay, because as you can see, these boxes you need uncountable intersection, which may not be in your sigma algebra. So in general, that's not true. Why do I care about the uncountable product space? Is because for those of you who come from math finance, you will actually often in time will look at the measures on the real line or sigma algebra. So on each time point, you have some random variable, and overall you have a product space. Okay, so a lot of times the lambda can be the real line, as basically it represents a time. Okay, and each of these B lambda kind of give you the measurable space for some random variable at a specific time, for example, the stock price at time t. And then you just build a product measure on the entire, this product, okay? So you can have a product of uncountably many of these sigma algebra. So that's why we do need this uncountable definition sometime. In any case, we don't really care too much when lambda is uncountable in this course. In fact, we're only going to do for Fubini's theorem, we're only caring about the product measure of two product space, of a two measurable space. So for this video, I just want to prove the first proposition we want to say. So suppose I have some xi and di, they are some metric space. And then let's just assume here I is going from 1 to n, so I have finitely many of them. Well, I can construct their product space, construct this product space of xi, should use big xi. Okay, and I can put a metric on it. So the metric, there are many ways of putting metric. So here I use one of them, is just you take the maximum of all the di of xi, yi, you take the coordinate, you get the distance, and you do the maximum. Okay, this is not the only one. You can do many creative ones as well, and most of them are going to be equivalent to each other, so they give you the same open sets. Okay, but in any case, anything equivalent to this distance or this measure, this metric, will have this property that if you take the pi, the coordinate map, the product space to xi is going to be continuous. Okay, that's the basically only thing we need for this metric. Okay, so now we have a bunch of metric space, and we have the product space, which is also a metric space. So we can talk about their Brown sigma algebra. So on one hand, we have the Brown sigma algebra on each of these metric space, and on the other hand, we have the Brown sigma algebra of the product metric space. Okay, so on this side, we can take their product. So here is the product sigma algebra of all these Brown sigma algebra. And this proposition, I'm going to show that they are actually the same. Okay, so the Brown sigma algebra behave pretty well under this finite product space. Okay, so here I forgot to mention, so I need one extra condition, so they cannot be just any metric space, they have to be separable. Okay, as you see, the separability is really important. Remember, when you prove the Brown sigma algebra on Rn is the same as the Brown sigma algebra generated by those closed cylinder sets, okay, that you need the separability. Okay, so this is in fact not true if you don't have the separable assumption. Okay, so the proof, one direction is easy. So if you want to prove the left is included in the right. Okay, so because these pi I is continuous, okay, we just take it for granted. So for every u open, let's say ui open in xi, then your pi I inverse of ui, the pre-image of an open set is open. That's just by definition of a continuous map. Okay, so this is open, so which is a cylinder set on the left. Okay, so it's open, so it's contained in the Brown sigma algebra of the product space. Okay, so it's open on the right-hand side, so it's inside the right-hand side. And the left-hand side is generated by all of the cylinder sets. Okay, so this proves this direction, this direction, so that's easy. Okay, the other one is slightly difficult. So for the other direction, so first of all, because each of these xi is separable, and by the way, we defined this distance on the product space by this definition, you can convince yourself the product of these xi is also separable. Okay, so that's an easy exercise. Okay. And let's just, because it's separable, let's give it a dense subset. So let's give it some name. So let's call it x bar. So x bar means a collection of x1 to xn here. So I go from 1 to n. Let's use the index, upper index, to denote I have different x bar. So here j is some sequence of such thing. This is dense. Okay, so I have a countably many of these elements, which is dense in the product space. Okay, dense in the product space xi. So let's denote something. So let's denote a box of these x bar j, and let's say some distance r bar. Okay, so here maybe I don't need the upper notation here. So here x is some xi, r bar is some ri. Okay, this is essentially just the product of the ball. Okay, the ball centered at xi with radius ri. Okay, that's understood in the xi. Okay, so that's in xi, and it's just the open ball. Okay, so you take their product. This one is inside the brow sigma algebra, the product of these brow sigma algebras. Okay, because each of these ball is open, so you take the product, and only taking finitely many of them. So it's a box, it's an open box, so it's inside this product sigma algebra. All right, and what I can do is I can make any open set a countable union of these boxes. Okay, so let's take for every U open inside the product space of xi. What I can do is that I can do the union of a lot of these boxes where I can make my the center of this box to be one of these dense elements. And I can make sure the radius, it may be over some different index. So here my requirement, so here the union's requirement is, first of all, these xij, the center has to be in U, of course. And when it's in U, you can pick some small numbers Ri, so that's still in U, but I want it to be a countable union. So I let all of these Ri, where it's equals to some, let's say the kth one, is basically have a bunch of these Ri, and I let each of these Ri of k inside the rationals. Okay, so positive or non-negative rationals. Okay, well, let's make it positive. You have to make it strictly greater than 0. Okay, so anyways, you need to make sure that this box is also inside this U. So we only take such box if such box is inside this U. Okay, so the union is taken over all such box inside this U, so that you know the union is a subset of U. And you choose the center to be one of the dense element, and you choose the radius to be any possibility. Okay, as long as all the radius is rational. Okay. So here, as you notice, for a fixed xj, you can have many different rk that makes this box inside U. You just take union of all of them. Okay, we're just taking a countable union. We don't care. And then they may be nested. We don't care. We just want to take a union. Okay. So why they are the same? I will leave it as an exercise. Okay, it's fairly easy to see why they are the same. Okay. But in any case, so this U is a countable union of these boxes. So this U is inside the brow sigma algebra of the xi and their product. Okay, so the right-hand side is included in the left, and we're done with this proof. And as an immediate corollary, because we know the real line under the usual metric is separable, so immediately we have the brow sigma algebra on the real line. As long as you're taking only finitely many of them, that's going to be the brow sigma algebra on Rn as well.